Now we are going to see about a complex analysis written by Bernard Riemann, number theory and differential geometry. I have got a topic residue theorem. I am going to explain briefly about a residue theorem and a proof of the theorem. Residue theorem has a four type of series: Cauchy's residue theorem, integral formula, calculus of residues, and a Lorentz series. Residue theorem, an analytic function whose Lorentz series is given by, it can be integrated term by term using a closed contour. Complex residue using the term residue theorem, calculus of residues. Suppose an analytic function f of z has an isolated singularity at z0. Consider an contour integral enclosing z0. If the contour encloses multiple poles, then the theorem gives the general result. We have given a diagram of the residue theorem. Here the complex variable f of z is equal to z cube by z minus 1 whole power 4, z minus 2, z minus 3. It is the residue theorem formula. Residue theorem, if the contour encloses multiple of isolated singularity, it is called as residue theorem. Here it is given as 2 pi I residue of f of z. Here we have the diagram of the vector calculus, zeros and poles, complex analysis, singularity meromorphic function, complex number. Calculus of residues, Cauchy's integral theorem and Cauchy's integral formula. We are going to see a brief of it. Cauchy's integral theorem, here summation an z minus z0 m is equal to f of z0. It shows the 2 pi I residue f of z0 is equal to 0. Cauchy's Gauss theorem says that if a function is analytic in a closed contour C, then it is 0. It is not analytic inside the contour. For example, we have f of z is equal to 1 by z minus 1, 1 plus z square. It is not analytic at 1 I minus I. Residue formula. To find a residue, we need to do the Lorentz expansion and the coefficient 0 to minus 1. We have a residue formula further. Here we have a formula a minus 1 is equal to residue f of z0 1 by m minus 1 factorial limit dm minus 1 by dz m minus 1. It shows that we have a residue theory f of z is equal to summation n to infinity minus infinity a n z minus z0 whole power n. It shows the residue at z0. Cauchy's residue theorem, we have a integral c f of z dz is equal to 2 pi I summation j to k equal to 0 at residue of f of z comma k. We have a diagram of a Cauchy's residue theorem where f of z to k, it shows a 0 o at the center of a circle and a c at a point. Cauchy's integral theorem, we have an f is a holomorphic function at a set S and it shows an pi r f is equal to 0 at Cauchy's theorem global. A formula proof of Cauchy's residue theorem written by Wendali and Lawrence Paulson. Here we have a holomorphic function where f is holomorphic, pi r f is equal to 2 pi I summation n k equal to 1 n into gamma ak residue f of a. For example, f of z is equal to 1 by z cube into z plus 4. It shows z square by 1 plus 4z, which is around positively oriented circle. Here we have another example of radius around the phi origin. Here shows 1 by z square f, 1 by z does not have a singularity at 0. It shows integral must be 0. Here we have an isolated singularity of f. Isolated singularity of f of z is equal to 0 at a condition 1 by sine pi by z. It shows f of z is equal to log of z. Using residue theory to evaluate infinisums written by Kegon-Kallis. Here the definition f to d to c is called as a holomorphic function if it is complex in a domain D. It shows e power I pi plus 1 is equal to 0 from complex analysis. Lorentz series generalizing power series in C, f of z is equal to summation n to infinity minus infinity a n z minus z0 whole power n. For an example, integral c 1 by z dz is equal to integral 0 to 2 pi 1 by e power I pi I e power I theta d theta is equal to 2 pi I. It shows a closed counter in a 0. Here it shows a finally summation infinity n is equal to 1 by n square minus 1 by 2 residue. It shows minus 1 by 2 minus pi square by 3. Here we have a summary of an holomorphic function, analytic and singularity are proved at a residue. It is a proof sketch of Cauchy's residue theorem by setting f of z is equal to 1 by z square. The core idea to induct on the number of singularity points, it forms a gap in informal proofs. Here we have a diagram. The proof of singularities integral theorem does not apply when there are singularities. It shows f of w is equal to 1 by w. It shows w is equal to 0 at a pole. Cauchy's residue theorem, Lemma residue theorem fixes at a point complex set and f of complex. It has a real point complex. Proof method 2. F of z is equal to summation n to z a power n z minus z naught of n. It shows that by the Taylor expansion. Here shown I is equal to integral 0 to 2 pi sin theta d theta by 1 minus a sin theta, where a is real at modulus a less than 1. We have a diagram of it. Hence the residue theorem have been proved. Thank you.